Good afternoon, everyone, and welcome to the next problem solving session for the course Fundamentals of Food Process Engineering. So, in this session, we'll be taking up problems related to week 8 syllabus, which includes size reduction. So, in this particular week, there'll be a lot of theory based questions and a little bit of numericals as well. Okay, so during the lecture, if you guys have any doubts, please let me know. We'll slow down and we'll take up those doubts as well. So, question 1, match the following. You have in the column first column, you have sorter diameter, Stokes diameter, surface diameter, and volume mean diameter. So, all these are kind of parameters that are used to characterize particles, your food particles. So, the diameters each of these diameters signifies a certain uh, length of the particle. So, you have those in column, the first column, and the second column you have the definition of these diameters. First, having the same surface area as that of the particle. Second, having the same surface to volume ratio of the particle. And then you have d equal to x1 d1, and 4 falling at the same terminal velocity. So, any clue which of these diameters correspond to which definition in the second column? Okay, we'll look at one by one. So, the sorter diameter is also known as surface volume mean diameter. And by definition, it means that the diameter of a sphere with the same surface to volume ratio as that of the particle. So, S by V of the particle should be same as the S by V of the sphere, and that sphere's diameter is known as sorter diameter. So, that is surface volume mean diameter. So, sorter diameter is basically this diameter of a sphere having the same surface to volume ratio of that as that of the particle. So, since particles are always majority of the time irregular in shape, you cannot actually measure a correct size because based on the orientation, the size will change. So, instead of looking at an irregular particle, we start to relate it with that of a sphere, and based on its relation with the sphere, there are multiple diameters involved. So, in sorter diameter, S by V of the particle equals S by V of the sphere, and that sphere's diameter is known as sorter diameter. So, the formula for that is DSV, which is the sorter diameter or surface volume mean diameter, is equal to sigma n1 d1 cube by sigma n1 d1 square. That is equal to 1 by sigma of x1 by d1, where n is the number of particles, d is the diameter or size of the particle involved, and x1 is the fraction of those particles. So, n is the number of particles, x1 is the fraction of particles. So, sometimes you have a mixture containing multiple kinds of food materials. So, in that case, if you're looking at a particle, let's say particle 1, at that time the fraction of that particle is called as x1, and the corresponding diameter is the d1. So, if you're looking at the second particle, it will be x2 by d2. So, if you have a uniform, if you have a mixture that contains only a single kind of a particle, then this will be x by d. Okay, so sorter diameter is this, and we move on to Stokes diameter. So, Stokes diameter, if you remember the Stokes law, it involves the calculation of something known as a terminal velocity. So, from Stokes law, you can calculate the terminal velocity of a particle, and this is something that we have discussed previously in multiple weeks. I think 2 or 3 weeks we have discussed already what is Stokes equation and how we can calculate the terminal velocity. So, when you mention something known as Stokes diameter, it is the diameter of a sphere that has the same terminal velocity as that of the particle. So, if a particle has a certain terminal velocity, say v, then the sphere will also have the same terminal velocity, and that sphere's diameter is known as the Stokes diameter. Next, in the column given was surface diameter. You can also call surface diameter as number surface diameter. So the definition of that is the diameter of a sphere that has the same surface area as that of the particle. If a particle has a surface area say S1, then your sphere will also have the same surface area S1, and that sphere's diameter is known as surface diameter or number surface diameter. And the equation for that is given by ds, which is the surface diameter notation, equal to root of n1 d1 square by sigma summation n1, where n is the number of particles, d is the size of that particular particle, which can also be given as summation of x1 by d1 divided by summation of x1 by d1 cube, where x is now the fraction of particles. And finally, volume mean diameter is also called as volume moment weight moment diameter. So that can be given as dV equal to summation n1 d1 4 by summation n1 d1 cube, which is equal to summation of x1 d1. So majority of these are discussed in the video lectures. There will be more like a short session, a short few minutes where the faculty has discussed all these diameters as well, and there will be a lot of problems related to these diameters that come in the assignments. The answer here is option C. To just verify here, Sauter diameter is the one that is having the same surface to volume ratio. Stokes diameter has the same falling at the same terminal velocity. Surface diameter has the same surface area as that of the particle, and volume mean diameter is equal to summation of x1 d1. So since this is pretty difficult to remember, there is a generalized formula for this. Let's say you have d q to p by q by p. Let's say this is the notation for a particular diameter. For that, the generalized formula is summation of d raised to q into n divided by summation of d raised to p by n. So first we need to see what is this q and p. We know d is the diameter, we know n is the number of particles, but we do not know what is q or p. So this q or p depends upon what is being asked in the question. So if you are talking about a number diameter, then you will substitute this value as 0. If you are talking about length diameter, then you will substitute it as 1. If you are talking about surface diameter as 2, volume as 3, and moment as 4. So each of these has a particular value of q and p. Number has 0, length has 1, surface as 2, volume as 3, and moment as 4. So let's say for an example, we want number length diameter, which means p will be equal to 0, q will be equal to 1. So when you substitute the number in p and q in the formula here, you will get summation of d into n divided by summation of d power 0, which is 1, into n. So automatically this will give you the number length diameter formula. So you don't have to memorize as long as you know this particular equation and what is being asked. So same way, let's say if you want the surface volume diameter, so P will be equal to 2, Q will be equal to 3. This is also known as the Sauter diameter, if you remember, the surface by volume ratio. So for Sauter's diameter, if you substitute P equal to 2 and Q equal to 3 here, you will get the formula for Sauter diameter as well. Same way for number surface diameter, you have number which is P equal to 0 and Q is equal to 2. Same way, if you substitute it back in the equation, you will get the equation for number surface diameter as well. So a much more detailed information is given in the PG Smith book that is being given as a reference in the NPTEL site as well. So instead of mugging up the formulas, you can also choose to use this particular equation. But it's always safe to remember the Sauter diameter and the surface diameter because these are the ones that are very commonly asked. Okay, is there any doubt in this? So the characteristics of the particles can be defined by different kinds of diameters because The particle as such is irregular in shape. So you connect it to a sphere and then calculate the diameter of that sphere. Okay, moving to question 2. The critical speed in a tumbling mill is A. The minimum speed required to reduce the size of the particle to a desired value. B. The speed required to reduce the size of the particle by half. C. The speed required to reduce the size of the particle by tenfold. And D. The speed at which centrifugation process is observed. So any clue what the answer to this question is? So before we proceed, we look at what a tumbling mill is. So this is how a tumbling mill looks like. You will have a cylindrical or a mill here, and you have a lot of large balls that are present inside the mill. And apart from these balls, now you will feed in your food product as well, and you will slowly rotate the mill. So upon rotation, you will see that the balls will first stick to the walls and rotate, and after a certain time, the balls will lose contact with the walls and then come and hit because of the effect of gravity. It will fall down because of the effect of gravity and because of the tumbling. So when you have food products placed here, as the balls fall down and hit, it will hit the food product, and that will result in the reduction of size of the particle. So when you have a very slow rotating speed, this is how your balls will fall. It will be sticking to the wall for a time, and since the speed is pretty pretty less, the balls will lose contact with the walls and fall down, hit the food and reduce the size. But if your speed is extremely fast, then what will happen is you will have the centrifugal force acting on the balls, because of which the balls will not fall down at all. It will keep sticking to the walls throughout if the mill rotates pretty fast. So the critical speed is the speed at which you see this centrifugation effect. That is, the balls, instead of falling down, will keep sticking to the walls because of very high speed. So just to summarize, in a tumbling mill, the balls act as a grinding medium, and the mill during the tumbling takes the balls along the walls up to a certain height, beyond which the ball falls back due to gravity onto the food particles, thus resulting in compression and attrition of the food particles. This causes the size reduction. And at the critical speed and higher, the tumbling speed is so high that the centrifugal force exceeds the gravity, resulting in centrifugation. The answer here is option D. Hope this is clear. We'll be having some problems related to this critical speed as well, which we'll be discussing in the further slides. Okay, moving to question 3. Which of the following mill works on the principle of both attrition and impact? You have A. ball mill, B. hammer mill, C. cutter mill, and D. pin mill. So any clue what the answer is? Yeah, the answer is A. So a ball mill is a type of a grinder used to grind and blend bulk materials into micro or nano sizes using different sized balls. And the working principle is based on that you have impact and attrition acting that helps in the size reduction as the balls drop from near the top of the rotating hollow cylindrical shell. Whereas just to explain what the rest of the mills are, you have a hammer mill where the hammer mill consists of a series of hammers. Here, all of these are hammers actually, and they are hinged to a central shaft. That is, they are connected to a central shaft and enclosed in a metal case. So as you feed the product, the hammer will hit these food products by the force of impaction, and because of this there is a reduction in size. So in a hammer mill, the main acting force is the impact. Whereas in case of ball mill, it's both attrition as well as impact. And then at the bottom you have the sieve with a specific diameter that will allow only the small size particles to come down and collect as the food product. And the other cutter mill involves the cutting or the size reduction uh, of the particle by with the help of knives. So you have involved successive cutting and shearing of the feed material with the help of sharp knives. And then after cutting you will have, again similar to how I showed in the hammer mill, you will have a sieve or a fibrous material or a mesh like material that will then collect these size reduced particles. And generally we use size reduction of tough and fibrous materials in a cutter mill. So in this case, it is a major cutting process that is the major force that is acting. And in the pin mill, this is how it looks. You will have tiny pins throughout attached on both the cylinders. And it is pretty similar to the hammer mill where you will have both impact and shearing. But then it will have much faster speed and you'll have pins instead of hammers here. So when you close this lid, your food particle will be stuck between these two rotating regions, which will have these intermeshing pins, and this will impact the particles as solids are directed through these pins. And after this, you will have your collection at the bottom. So the answer here is option A, which is the ball mill, which includes both attrition as well as impaction. So question 4. Crushing efficiency is the ratio of A. Energy absorbed by the solid to the surface energy created by crushing. B. The energy fed to the machine to the surface energy created by crushing. C. The energy absorbed by the solid to that fed to the machine. And the surface energy created by crushing to the energy absorbed by the solid. So which of these is the correct answer? Yeah, D is the correct answer, where crushing efficiency is the ratio of the surface energy created by crushing to the energy absorbed by the solid. So if you want to look at the crushing efficiency formula, here Wn equal to Es AWB minus AWA by eta C, where Es is the surface energy per unit area, AWB and AWA are area of a unit mass of the product minus that of the feed, divided by eta C, which is the crushing efficiency, and Wn is the energy absorbed by the unit mass. So this ES into surface energy per unit area into area will give you the surface energy created by crushing, divided by Wn, which is the energy absorbed by unit mass, is equal to eta C, which is the crushing efficiency. And generally what happens is that majority of the energy that is absorbed by the solid will not be converted into surface energy by crushing. There will be a lot of energy losses due to heat and other stuff, because of which the crushing efficiency is pretty low. In majority of the cases it is extremely low. You will have somewhere close to only 1% or 2% or so, because majority of the energy is lost due to heat and other losses are also there. Okay, question 5. What happens in attrition mode? A. The blades are used for size reduction. B. A forceful object strikes a stationary object. C. Force is applied by the means of a hammer. And D. Rubbing the material between the two surfaces. So what describes an attrition force here? No, if you remember, the hammer mill works by the force of impaction. So in order to understand it better, impaction is basically you have a substance that is coming forcefully on your food material. Like say you are hammering a food product. So hammer is involved in impaction. Attrition is that you have food products here and you have two forces acting in the opposite direction. Basically, like rubbing. If you have something between your palms and you keep rubbing it, that process is known as attrition. You have one force acting in this direction, one force acting in the other direction, and it is continuously rubbing the food material between these two forces. So this is known as attrition. And in shear, you have a force tangential to the surface of the food particle. So that is known as shear, and it is generally only in one direction. And compression, you have on both the ends acting normal to your food, normal to the surface of your food particle. So here, and cutting involves cutting or using blades for size reduction. So these are majorly the kinds of forces that we will be discussing in the video lectures as well. So attrition involves rubbing or wearing down due to friction. The material is pulverized between the two tooth metal discs rotating in the opposite directions. So this is what attrition looks like. And hammers is what results in impaction. The answer here is option D. Question 6. The critical speed of the ball mill of radius capital R, which contains balls of radius small r, is proportional to r minus r raised to minus 0.5, r minus r raised to minus 1, r minus r, and r minus r the whole square. So if you remember, the critical speed is the speed at which you can start seeing a centrifugation process happening instead of the balls falling and hitting your food particle. So any clue what the critical speed is proportional to? Okay, the critical speed of a ball mill can be given as capital NC is equal to 1 by 2 pi root of G divided by R minus R, where G is a gravitational constant 9.81 meter per second square. Capital R is the inside radius of the mill, the ball mill, and small r is the radius of the balls that we have inside the mill. So this gives you the critical speed in RPS, that is revolutions per second. So the derivation for this formula is given in the video lectures, and it basically involves the force balance between your centrifugal force and your gravitational force. So if you do a force balance of the balls from the by equating the centrifugal force to the gravitational force, you can get this critical speed of the ball of the mill. So your NC is directly proportional to R minus R raised to minus 0.5, which is option A. If there is any doubt, kindly let me know. We'll repeat that question again. Work index in Bond's law for crushing has the following dimensions: A. No units, B. kilowatt hour per time, C. kilowatt per time, and D. kilowatt hour meter raised to half per time. So before we proceed, any clue what Bond's law is? Okay, so in the upcoming slides, we will be discussing different kinds of empirical laws that relate the energy consumption to the size reduction involved. So, in order to reduce the size of a particle, you need to provide some energy, either to the balls, to the mill, to the hammer, something. So, there is some kind of an energy consumption that happens, and based on how much fine you want the particle to be, how much small you want a particle to be, your energy consumption will also differ. There are multiple laws involved to calculate this energy consumption based on the size of the particle, that is your final particle size and the initial particle size. This will influence the energy consumption. And one of the laws involved in calculating this energy consumption is Bond's law. We'll be discussing in much greater detail in the coming slides. So numerically, the work index is the energy required in kilowatt hour per time to reduce a given material from an infinite feed size to 80% passing 100 microns. Which means that, let's say your food particle that you're initially feeding inside the instrument is of an infinite size. And the final size of the food particle will be 100 microns. Okay, but only not 100% of the particle needs to be 100 microns. 80% of the food particles, if it is 100 microns, it is enough. So the energy required to reduce the size from an infinite size to 80% of the particles being 100 microns. This is known as the work index. And since work index is the energy required, the units is in kilowatt hour per time. So the work index of a particular material can be determined in the laboratory by conducting something known as a bond grindability test. The answer here is option B. That is from infinite size to 100 microns, where 80% of the particles have this size. We will be solving some numericals regarding this work index as well. Hope this is clear. Any doubt on this? Okay. Moving to question 8. A ball mill of 1.5 meter diameter is charged with balls, each having a diameter of 5 centimeter. The rotational speed of the ball mill is kept at 70% of its critical speed. We need to calculate the operating speed in RPM. So how do you proceed with this? So given here, the diameter is given of the ball mill. So we are calculating the radius, which is, let's say, capital R, that is equal to 0.75 meters. Then the diameter of the ball is given, and we are calculating the radius of the ball, which can be given here as small r, that is equal to 2.5 centimeter, also equal to 0.025 meters. And it is given in the question that the speed of the ball is kept at 70% of its critical speed. So V is equal to 0.7 into Nc, where Nc is the critical speed, V is the rotational speed of the mill. So if we remember the formula for the critical speed, Nc is equal to 1 by 2 pi root of G by R minus R, where G is a gravitational constant, R is the radius of the mill, capital R is the radius of the mill, and small r is the radius of the ball. And the Nc that you will get it in revolutions per second. So I am just substituting the values here. We already have all the parameters that are required to calculate the Nc. So 1 by 2 pi root of 9.81 meter per second square, capital R as 0.75 meters, and small r as 0.025 meters. So if you substitute the values of this and calculate, you get a capital Nc of 0.585 rps. So this is your critical speed in revolutions per second. But the question here is asking in revolutions per minute. So I am multiplying this into 60, and if I multiply this into 60, I get 35.1 rpm, which is revolutions per minute. Now this is just the critical speed, but the rotational speed is maintained at 70% of the critical speed. That is your operating speed. So the operating speed is equal to 0.7 into Nc. I am substituting the value of Nc that we calculated here. That is equal to 0.7 into 35.1 rpm, which gives me 24.6 revolutions per minute. This is option B. Any doubts in this? we'll move on to question 9. A crushing roll of diameter 1 meter. This is the crushing roll. So you have two cylinders here that will rotate in the opposite directions. One will rotate in the clockwise, the other one will rotate in the anti-clockwise. You will have your food particle coming in, and if your food particle is small enough to get in between these two cylinders, it will come in between and it will be crushed, and then you will have size reduction happening. So you can't just directly add any food particle of any size. It has to be small enough to get in between these two cylinders. That is what we are going to calculate here. A crushing roll of diameter 1 meter are 12 millimeters apart. So this diameter is 1 meter and they are 12 millimeters apart. So this distance is 12 millimeters. The angle of nip is 30 degrees. The maximum size of the particle that can be fed to the rolls is dash. So what you mean by angle of nip is that this particular angle, if you draw a tangent here, and if you draw a tangent here, that is the point at which the particle is touching the first roller. So you draw a tangent here, and the point at which the particle is touching the second roller. So you draw a tangent at this. So when the two lines intersect, that angle is known as angle of nip, and that is always equal to 2 into alpha. So if you draw a tangent here and you draw a tangent here, and wherever those two lines intersect, that angle is called as 2 alpha and also known as the angle of nip. So given in the question is that we know what is the diameter of the roller, which is R1 is given here. So R1 is 0.5 meters. Diameter is given. I've calculated the radius, 0.5 meters. We know that they are 12 millimeters apart. That is 2b is equal to 12 millimeters. So b is equal to 0.006 meters. And the angle of nip, which is 2 alpha, is 30 degrees. So alpha is equal to 15 degrees. So if you want to calculate R2, we can that is what is asked in the question. So this is the food particle here, and we need to find out what is the size of the particle. So we can find out by basic trigonometry that we know. So cos alpha here, let's look at this particular triangle. The cos alpha here is equal to R1 plus B, which is in the numerator, divided by R1 plus R2. So that is adjacent by hypotenuse will give you cos alpha. So adjacent is R1 plus B, hypotenuse is R1 plus R2. That will be equal to cos alpha. We already know what is alpha. We know what is R1 here, which is the diameter of the roll. We know what is B here. We have to calculate what is R2. So this is basic substitution substitution problem. So cos 15 is equal to 0.5 plus 0.006 divided by 0.5 plus R2, which is still unknown. So from this we get R2 as 23.8 millimeters. So when you mean the size of the particle, it always means the diameter of the particle. So diameter is twice the size of the radius, which is 47.6 millimeters. The answer here is option C. So hope this is clear. If there is any doubt, kindly stop me. We will repeat that part again. Okay. So moving to question 10. Statement 1. According to Rittinger's law, the energy required is proportional to the linear dimension, and statement 2, Rittinger's law is more accurate for fine grinding. So which of these statements is true or false? Any clue what a Rittinger's law is and if statement 1 is true or false? Okay, so no, statement 1 is actually not true. So we look at the three different kinds of loss. So the energy change required for the size reduction of a particle. So let's say the energy change required is dE, or energy consumed is dE, to reduce this particle by a small change dx. So dE by dx is directly proportional to the size of the particle, and this is by a power law model. So dE by dx is equal to minus c x bar minus m. So here you have a minus because there is a size reduction happening. So with increasing energy, you are reducing the size, that which is why you have a minus sign here. So dE by dx is equal to minus c x bar minus m. So as I told you before, there are three different empirical laws that we'll be discussing, and that law will based on the law, your m values will change. C is a constant. Your m value will change based on the law that we are looking at. So according to Rittinger's law, m is equal to 2 here. That is, the energy required is proportional to the surface area of the particle. If you have x square here, where x is the dimension of the particle, c is a constant, x is the dimension of the particle. So if you have x square here, which means that the energy required is proportional to the surface area of the particle. Hence, Rittinger's law, energy is required is proportional to the surface area and not the linear dimension. So hence statement 1 is false. So basically I am substituting the m as 2 here. So you have dE by dx is equal to minus c x bar minus 2. Now I am integrating the equation from 0 to e dE equal to minus c integrating x bar minus 2 dx from xf to xp, where xf is the size of the feed that you are sending in and xp is the size of your final food product that you are taking out. So from xf to xp you are reducing the size. So upon further simplifying and carrying out the integration process, you get x bar minus 1 divided by minus 1 here upon integrating this particular RHS. So on simplification and applying the limits, you get E is equal to Kr, which is the Rittinger's constant, into 1 by xp minus 1 by xf, where xp is the dimension of the product particle and xf is the dimension of the feed particle. So Rittinger's law is based on the fact that energy consumption is directly proportional to the surface area and not the linear dimension. So statement 1 is false, and this law is used for in cases of fine grinding. That is, when you want to finely grind your particle and xp is very less than xf, at that time you use Rittinger's law, which is much more accurate. So hence statement 2 is true. So answer here is option E. Okay. Moving to question 11. Rittinger's law is applicable only when A. New particles are created, B. New surface area is created, C. Energy is created, and D. Energy is absorbed. So which of this statement is correct? Yeah, so since Rittinger's law, where the energy consumption is directly proportional to the surface area, it applies only when you break down and you have a newer surface area right now. If you break down the particle and now that particle has a new surface area, that is when you can apply Rittinger's law. And this holds for fine grinding, where an increase in surface area per unit mass is large. The answer here is option B. Okay, question 12. So here in this particular problem, we will be discussing all the other empirical laws also involved apart from Rittinger's law. So which of the following is incorrect? Bond's law is for intermediate grinding. According to Bond's law, the energy is directly proportional to the size reduction ratio. See, Kick's law is for coarse grinding and assumes M is equal to 1. Rittinger's law is for fine grinding and assumes M is equal to 2. So any clue which of these statement is incorrect? No, A is actually correct. So we look at different laws. So as I told you, this is common for all the three laws. That is, the energy change required to reduce the size dE by dx is directly proportional to the size of the particle. So if you remove the proportionality constant, you have a minus c here. So dE by dx is equal to minus c x bar minus m. And this follows the power law model. So in Rittinger's law, which we saw before, it applies for fine grinding where energy is proportional to the surface area. So since it is proportional to the surface area, we are looking at x square here. So m is equal to 2. And in case of Kick's law, which is applicable for coarse grinding, energy is proportional to the linear dimension or size reduction ratio. So it is only proportional to the length of the particle and not any area or volume. So for Kick's law, since it is only proportional to the linear dimension, m is equal to 1 here. And that is applicable in the case of coarse grinding. And Bond's law is applicable for intermediate grinding, where energy is proportional to the square root of the surface volume ratio. So in that case, m is equal to 3 by 2. So the statement A is correct. Bond's law is used for intermediate grinding, but in Bond's law, the energy is directly proportional to the square root of surface volume ratio and not to the size reduction ratio. In case of size reduction ratio, it becomes Kick's law. And for Kick's law, it is used for coarse grinding and assumes m equal to 1, which is also true. And as we discussed before, Rittinger's law is for fine grinding and assumes m is equal to 2. So here m is equal to 1, it is m is equal to 2. So statement B is incorrect. So these are the three laws that we'll be using, and there will be certain numericals also connected with these empirical laws, which we'll be discussing in the upcoming slides. Okay, hope this is clear. For Kick's law, m is equal to 1. For Rittinger's law, m is equal to 2. And for Bond's law, m is equal to 3 by 2. So you can just substitute m in this equation, integrate it, and get the formula for each of these laws. Okay, question 13. A roller mill converts 100 kg per hour of wheat grits into flour. If the Bond's energy constant for wheat grit is 3.02 kilowatt hour millimeter per raised to half ton inverse, the power required for grinding the grits from an average particle diameter of 3 millimeter to 0.1 millimeter is dash. So here we already know the Bond's energy constant is given, which means that we have to use the Bond's law. So in Bond's law, if you remember, we will be substituting the m is equal to 3 by 2 here. If you then integrate this, you will get minus 3 by, you will get x bar minus half by minus half if you integrate this. So I am just giving you the direct formula here, where energy is equal to 2 into C, which is some constant, the same constant that we see here, the C constant here. So energy is equal to 2 into C into 1 by root of xp minus 1 by root of xf, where C is the constant that we saw in the previous equation, that it was dE by dx is equal to minus C x bar minus m. So that is the C here. xp is the dimension of the product and xf is the dimension of the feed particle. So that is equal to energy here. And this energy is actually can be seen as power per the mass flow rate. So Bond's law here is given as P by M, equal to 2c into into 1 by root of xp minus 1 by root of xf. So when you mean Bond's energy constant, this entire part outside the bracket 2c is the Bond's energy constant. So you can call it as Kb here. So this entire constant is known as Bond's energy constant, which is given as 3.02 in the question. The mass flow rate of the wheat grits is given as 100 kg per hour. The xf, which is the particle diameter of the feed, is given as 3 millimeter. We are reducing it to 0.1 millimeter. So this is just basic substitution here. But what we need to keep in mind is that the units of this Bond's constant is different. You have in millimeters and you have it in tons. So you make sure that the rest of the parameters are also in our unit wise consistent. So here M here is in tons per hour and power is in kilowatt. So I am now substituting the values. P is equal to 100 kg per hour. I am converting it into tons, which is 0.1 ton per hour. I am substituting it here. 2C or the Bond's constant is given as 3.02 kilowatt hour millimeter per half into ton inverse. So I am substituting it as 3.02. Since all of these are in millimeters, I will be substituting XP and XF also in millimeters to maintain consistency. So XP is 0.1 millimeter, XF is 3 millimeters. So hope this is clear till now. From there I am getting power as 0.78 kilowatts, which is option B. Any doubt in this? So if you just substitute M is equal to 3 by 2 and integrate, this is the equation that you will get, where 2C is the Bond's constant. Similarly, you will have multiple questions for Kick's law also and for Rittinger's law also. So based on that, you substitute either M is equal to 1 or 2, integrate it and then substitute the values. Moving to question 14. Which of the following is commonly used for the extraction of sugarcane juice? A. Serrated crushing rolls, B. Jaw crusher, C. Gyratory crusher, and D. Hammer mill. So what is the answer to this question? If you have ever... No, jaw crusher is not used. If you have seen in the roadside stalls, the preparation of sugarcane juice is by passing the sugar canes through a kind of a cylindrical roller which has serrated surfaces. So yeah, if you the answer is option A. So you have two cylinders with serrated tooths here on the surface, and you pass your sugarcane through these cylindrical rollers, and because of these serrated tooths, your sugarcane will be crushed and then you will get the extraction of sugarcane juice. The serrated crushing rolls have two cylinders with jagged surfaces that rotate in the opposite direction. The food is placed between these two rolls and the size is reduced as a result of compression, impact and shear. And this is commonly used for sugarcane extraction, juice extraction. In the case of a jaw crusher, it is majorly compression involved, while you will have a V-shaped jaw-like instrument. Your food will pass between this V-shaped material and your jaws will keep opening and closing to crush the material. In case of a gyratory crusher also, you will have a conical instrument that will be constantly shaking here and there, and this conical surface will hit the walls and it will hit the food particle also. So because of this gyratory motion, the food particles will keep hitting against the gyrating surface, and then you will have a reduction in the size. So the diagram of this is already, so this is the diagram of a jaw crusher, where you have a V-shaped particle and the jaw will keep opening and closing to reduce the size. Whereas in case of a gyratory crusher, you have a surface here that will keep constantly shaking, and the food particles that are stuck between the shaking region and your outside metal part, that is the mill and your shaking region, the heating will happen here, and then you will have a reduction of the size particle. And in case of the hammer mill, as we already saw in the first slide, you will have food particles coming in, and hammers will be constantly rotating, which will hit the food particles, and then you will have a reduction in the size. Here the answer is option A. Okay, question 15. A cylindrical shaped food material has a length and diameter of 12 millimeters and 8 millimeters respectively. You need to calculate the equivalent surface diameter. So how do you proceed with this? So if you remember what the equivalent surface diameter is, it is the diameter of a sphere that has the same surface area as that of your food particle. So you calculate the surface area of your food particle, that will be the same as the surface area of the sphere. From there you back calculate the diameter. So that is the procedure for these kinds of problems. So the equivalent surface diameter is the diameter of a sphere having the same surface area as that of the particle. So here we know that the particle is cylindrical in shape. So the surface area of the cylinder can be given as 2 pi r into r plus h. So we know the length is given as 12 millimeters, which is h here. Diameter is 8 millimeters, so radius is 4 millimeters. The surface area of the cylinder can be given as 2 pi into 4 plus 12. So this gives me the surface area in millimeter square, which is 401.92 millimeter square. So since it's a cylindrical shaped food, you are calculating the surface area of the cylinder with the help of the formula, and you get the answer as 401.92 millimeter square. So now you know that the sphere that you are looking at also has the same surface area, which means that surface area of the equivalent sphere is equal to surface area of the particle. And surface area of the equivalent sphere can be given as the formula as pi d square. That is also equal to 401.92 millimeter square. From there, if we calculate the diameter, we get 401.92 divided by pi, and you take a root of it, you get the diameter, which is 11.31 millimeters. The answer is option D. Any doubts in this? Okay, so moving to question 16, we'll have a similar this thing. A cylindrical shaped food has the same dimension as in the previous question. So 12 millimeter length and diameter 8 millimeter. Now we need to calculate something known as sphericity. So what is the definition of sphericity? So sphericity can be given as surface area of the sphere having the same volume as that of the particle divided by surface area of the particle. So in order to calculate the sphericity, what you need to do is, first we need to calculate the volume of the particle, then that will be the volume of the sphere as well. From there you calculate the diameter of the sphere and then calculate the surface area. So both the sphere and your particle has the same volume. So you equate the volume, and from that you calculate the surface area of the sphere. And that is divided by surface area of the particle. So from the previous problem itself, since the dimensions are the same, I am taking the answer from the previous problem itself. The surface area of the particle we calculated as 401.92 from the surface area of the cylinder equation, which is 2 pi r into r plus h. So we know what is the surface area of the particle. So we have the diameter, we have the denominator. Now we need to calculate the volume of the particle. Since we are looking at a cylinder here, the volume of the particle can be given as pi into r square h. So I am again substituting the values here. This pi into 4 square into 12, which gives me the volume as 602.88 millimeter cube. So now we have the volume of the particle. Now your sphere also has the same volume as that of the particle. And the volume of a sphere can be given as pi by 6 into d cube, which is equal to 602.88. From there we calculate the diameter. We get it as 10.5 millimeter. So now that we have the diameter of the sphere, we finally need to calculate the surface area of the sphere. So surface area of the sphere is equal to pi d square is equal to pi into 10.5 millimeter square, which we now found out. So surface area comes out to be 346.19 millimeter square. So now the sphericity is equal to surface area of the sphere by surface area of the particle. So 346.19 millimeter square divided by surface area of the particle 401.92 millimeter square. If you divide both of it, you get sphericity as 0.86. Answer is option A. Any doubt in this? The definition of sphericity? If there is any part that needs to be repeated, kindly let me know. We'll repeat that part again. Moving to the next question. Question 17. A material is milled from 15 millimeters to 2.5 millimeter using an 8 kilowatt motor. What size motor will be required to reduce the size now to 0.2 millimeter using Kick's law? So given here, for the first case scenario, XF is 15 millimeter, XP1 is 2.5 millimeter, and the energy for that particular size reduction is 8 kilowatt. Now for the second case scenario, we need the XF remains the same, but the XP is 0.2 millimeter. So for this particular scenario, we need to calculate what is the energy, and we already know that we have to use the Kick's law. So if I am substituting the value in that particular equation where dE by dx is equal to minus C x power minus m. So in Kick's law, you substitute m is equal to 1. And when you substitute m is equal to 1 and integrate from xf to xp, you get energy consumed is equal to kk, which is the Kick's law constant, into natural logarithm of xf by xp, where xf and xp are the sizes of the feed and the product particles, kk is the Kick's constant, and E is the energy required. So this is the formula for Kick's law. So now for the first case scenario, we have what is XF, we have the XP, we have the corresponding energy as well. But we do not know what the Kick's law constant is. So we can calculate the Kick's law constant by substituting the parameters for the first case scenario. So 8 kilowatts is equal to kk into ln of 15 divided by 2.5 XF by XP. From this, we can calculate the Kick's law constant as 4.46 kilowatt. Now, the Kick's energy constant remains the same for a particular product. If you are dealing with a certain kind of product, say wheat or rice or something, for that particular product, your Kick's law will remain constant irrespective of how small you want to reduce the size. So, it doesn't matter what XP and what XF are. If you are dealing with a certain kind of product, the Kick's law remains constant. So now in the second scenario, you have the Kk here, you know what is Xf, you know what is Xp. From there you can calculate E in the second case scenario. That is what we'll be doing here. So Kick's law constant we calculated as 4.46, Xf is 15 millimeter. Now you want to reduce it to 0.2 millimeter, which is Xp. So for the second case scenario, if you just substitute the values and calculate, you get energy as 19.3 kilowatt. This is option C. So basically, for the past 2 years, you will have assignment problems related to at least one of these three laws that we have been discussing so far. Okay. So going to question 18. The work index of a material is 5.85. If 80% of the feed and 80% of the product can pass through the seam opening of 3500 micrometer and 450 micrometer respectively, the power consumed to crush 120 kg per hour of sorghum is dash. So if you remember what we discussed about work index is used in Bond's law, where M is equal to 3 by 2. That is, your energy consumption is directly proportional to root of the surface to volume ratio. So M is equal to 3 by 2. So when you look at the term work index, it means you need to use the Bond's law. So Bond's law is given as we discussed again before, E is equal to power by mass flow rate, which is also equal to 2C, where 2C is the Bond's law constant, into 1 by root of Xp minus 1 by root of Xf, where Xp is the size of the product, Xf is the size of the feed material. But here we have what is Xp and Xf. We know that your product is 450 micrometer and Xf is 3500 micrometer. But we do not know what is C here. But we have capital M, which is the mass flow rate given as 120 kg per hour. And we need to calculate the power. But in order to find out the power, we still do not know what is C here. Instead, we are given the work index in the question. So if you remember what the definition of work index is the energy required to reduce unit mass of a material from infinite size to a size where 80% of the material is below 100 micrometer. So work index is the energy required. So if you substitute E as Wi or the work index notation, so that is applicable when Xf is infinity. That is, the size of your feed is infinity and size of the product is 100 micrometer. So if you substitute Xf as infinity, this entire term will go to 0. And if you substitute Xp as 100 micrometer, then your E will be equal to Wi. So I'm just showing it here. So when E is equal to Wi, so this is not kb, this is C here, sorry. So Wi is equal to 2C into root of 1 by root of 0.1 minus 1 by root of infinity. So this is how this is the definition of work index. So this entire term goes to 0 and you have 2C is equal to root of 0.1 into Wi. So this is the relation between your Bond's law constant and your work index. So now that work index is given in the question, you can calculate what is 2C and you can substitute back inside the equation. So 2C is equal to 0.3162 into Wi, which is root 1.1 is equal to 0.3162 into Wi, and I'm substituting it back inside the Bond's law equation. So instead of 2C, I'm substituting it as 0.3162 into Wi into 1 by root of xp minus 1 by root of xf, and that is equal to your power by mass flow rate. We have Wi given in the question. We know what is the size of the feed, we know what is the size of the product, we know the mass flow rate, from where we can calculate know the power. So power is equal to m, which is 120 kg per hour. We need to convert kg per hour into tons per hour. So 120 kg per hour is also equal to 0.12 tons per hour into 0.3162 into work index given as 5.85 in the question, and xp is given as 450 micrometers. So micrometers is being converted into millimeters. So 0.45 is the in millimeters, and you have 3500 micrometer as the size of your feed. That again I am converting it into millimeters, which is 3.5. So when I substitute the values and find out, calculate, I get P is equal to 0.21 kilowatt. Answer is option D. Is there any doubt in this? What is a work index? So the moment you have something called as work index, you have to definitely use only the Bond's law. Any doubts so far? Okay. Moving on to the last question. Calculate the fineness modulus given the particle size analysis. So in column 1, this is given in the question. Column 1 you have sieve number, and column 2 you have the weight retained. So what happens in a sieve analysis is that you have multiple sieves arranged on top of each other. Sieve is like a mesh of different sizes or different diameters. So if your particle size is smaller than that of the sieve size, then your particle will pass through that mesh. But if your particle is bigger than that of the sieve size, it will be retained and it will not pass through the mesh. So you have sieves arranged one on top of the other, and on the top you will add your food particle and you will keep shaking it. So all the particles that are of smaller size than 100 micrometer, let's say 100, will go down to the next. Particles that are smaller than 50 will go down to the next, then it will go down to the next, then it will reach the final collection pan where we collect the particles. And particles that are larger than this particular size will be retained in these sieves. So hope this is clear. You will have multiple stacks of sieves. You will pass the food particle on the top. You will keep shaking it. Smaller the particles, more it will be able to pass through the sieve and be collected in the pan. If it is large enough, it will be retained in that particular level itself. So we need to calculate what is the fineness modulus, or how fine the particles are. And we have in each of these sieve numbers, you have 10 grams of the product retained. In the sieve number 50, you have 18 grams of product retained. In 30 sieve number, you have 26 grams of the product retained. So these are all bigger in size, so which is why they are retained. And in sieve number 15, you have 34 grams retained. And in the final collection pan, you are getting 12 grams. So fineness modulus, by the definition of fineness modulus, it means that it's an empirical number obtained by summation of fraction of weight retained in the sieve multiplied by the sieve stage. So the fineness modulus gives an idea of the coarseness or the fineness of the product. Lesser the value, more fine the product is. So since the definition is pretty complex, we'll break it down one by one. So it is the summation of, so you basically have to sum the fraction of weight retained in each sieve multiplied by the sieve stage. So let us look at the table again. So instead of you had the seed number given and you had weight retained given in the question. So how you do this is that you assign a stage for each of these sieve. So always your pan will be stage 0. and from the bottom you have to go to the top. So this will be stage 1, this will be stage 2, this will be stage 3, and this will be stage 4. So always start from pan as 0 and work your way upwards as 1, 2, 3 and 4. So this is how you assign your stage to each of your sieves. Okay. And if you remember the definition given, it is the summation of your fraction of particles retained into your stage. So fraction of particle means you need to first do a summation of all these weights. So 10 plus 18 plus 36 plus 34 plus 12 gives you a total of 110 grams. So when you mean fraction retained, it means 12 divided by 110 is what is retained in the pan. 34 divided by 110 is what is retained in sieve number 15. 36 by 110 is retained in sieve number 30. 18 by 110 is retained in sieve number 50. 10 by 110 is retained in sieve number 100. So this is the fraction of weight retained. That into sieve number is what is done here. So fraction of the weight retained into sieve stage. So sieve stage is 4 into fraction of weight retained, which is 10 by 110. If you do this, we get a value of 0.3636. For the next stage, you have sieve stage as 3. Sieve stage as 3, and you have the fraction of weight retained as 18 into 110, which is equal to 0.4909. Then again sieve stage, which is 2 here, into fraction of weight retained 36 by 110, which gives you 0.6545. Then sieve stage number 1 into 34 by 110, which gives you 0.3091. And for pan, since the stage is 0, this is equal to 0 into 12 by 110, which is also equal to 0. So now you add all these values. This is summation of weight of fraction into sieve stage. So you add 0.36 plus 0.49 plus 0.65 plus 0.30 plus 0, which gives you the value of 1.81. So your fineness modulus is equal to 1.81. This is how you calculate the fineness modulus. A similar problem has also been discussed in the video lectures as well. So any doubt in this table formulation? How do you calculate these? Answer here is option B. So with this, we wind up this week's problem solving session. If there is any doubt in any of the questions before, please let me know. We'll take up that question again.